of all, you can consider this as a function, f of x equals 1 over 1 minus x. And as you know, this series here converges to 1 over 1 minus x, or that if there's an r. And that's this is going to work if absolute value of x is less than 1. Okay, or namely between negative 1 to 1. Okay, this is going to work. So this function here, 1 over 1 minus x, can be represented as this power series. Now, in general, okay, down here I have a whole bunch of power series of different functions. So sine x is represented by this, cosine x by this, inverse tangent x, and so on. Exponential logarithm of 1 plus x, and then the binomial series right here. Now, generally what happens is, let's say that you had a function and you want to figure this out. So let's look at this right here. So how do they come up with all these? Well, one way is by doing this formula right here. And let me show you how that, let me just show you briefly how that works. Because sometimes it's faster to just do it this way. Okay, so let's suppose that you have a function, you have f, okay, and you want to find the series. You want to find this, okay, you want to find this, the series. Okay, so what happens is you have f of x equals all this, and if you can look at it like this, or you can look at it in this terms. And for what I'm about to do, it's best to look at this one right here. Okay, so and this has to be true for all values of x. So you set x equal to a, which is the center point right here, and the left-hand side, the side right here, is going to give you f of a, and over here, this is, when you put an a here, this is gone. You put an a there, that's gone. All these things are gone, and you just have C0. Okay? So that's telling you that C0 is f of a. Now, for the next step, you take derivatives with respect to x, okay, of this and that. So taking the derivative of this, you get f prime of x. Taking the derivative here, this goes away. That's just gone. And then, so that's 0. And then the derivative of this is just C1. The derivative of this one, you use the power rule, the power chain rule. So a 2 comes down. And this is reduced by 1. For this one, a 3 comes down. And this is reduced by 1. For this one, a 4 comes down, and this is reduced to a 3. And then you continue that pattern. And then at this point, you set x equal to a again. And this is going to give you f prime of a equals C1. Okay, so C1 will be f prime of a. Okay, so remember you have f, so you can take its derivative and find, and then that's going to be the term. That's going to be the C1 term. Okay, and then you take a derivative again, the second derivative, and that, so it's the derivative of the first derivative. That's gone, that's gone. You get 2 C2 plus, and then a 2 comes down, so that's 3 times 2. That reduces to just an x minus a. And then this is for a 3 comes down from here. And you set x equal to a again. And you have the second derivative of a is equal to 2c2, because that goes away, because putting an a here also makes that go away. And so c2 would be f double prime of a over 2. Now in general, this is what you're going to get. So if you go another step, if you repeat this process again, you're going to have c3 will be f triple prime of a over 3 factorial. So that's, you got 3 times 2. And then this one's going to give you 4 times 3 times 2, 4 factorial. Okay, so the c4 will be the fourth derivative of a at valued at a divided by 4 factorial from here. Okay, so this is the formula that you get. And here's the different functions that are useful. There's the sine, cosine, inverse tangent. Now, if you see things that are similar to any of these or similar to this one, then sometimes you can use these formulas, or a lot of times you can use these formulas to help you find something that's similar. So let me do a few examples. Unless there's any questions at this point. Any questions before we go to the next, before we continue? Okay, let's go on to the next page. So here again, we have 1 over 1 minus x. This is just the same thing right here. And for this section 11.9 that we're doing, keep in mind that all the power series are related to the geometric series, are related to this series here. So we don't quite get into these ones yet. Although the logarithm and the inverse tangent function are actually related to this one. And I'll show you why in a little bit. But first of all, they're actually related because of some manipulation and because of integration and differentiation of series. Okay, so one thing about integration and differentiation is it basically works on as you'd expect. Okay, so if you have a power series representation, it's pretty straightforward to take a derivative or an integral, and things work out as expected. And also, the radius of convergence doesn't change when you take a derivative or an integral. Although the interval might change. That means just the endpoints. The endpoints might change, they might not. If you take a derivative, then you might lose an endpoint. If you take an integral, you might gain an endpoint. Okay, so the interval can change, but not the radius. The radius is going to stay the same. And here, the radius for this one is 1, because this converges when x is less than 1 in absolute value. Okay. So let's suppose that we have a power series. This is what I mean by integration and differentiation. So here's your power series. G of x is Cn x to the n. The derivative, you just take the derivative of each term, and that's going to give you n Cn x to the n minus 1. Okay, just taking derivatives of that. And that's going to be, and that'll be the series of the derivative of g of x. The integral, pretty much the same thing. Take the integral of each term. You get that. So the integral of x to the n is xn plus 1 all over n plus 1. So that is the integral right there. And so what I said before about the endpoints, if you take a derivative, you have this n coming down, which makes it harder to converge. but it only really applies to the endpoints. And then when you take integrals, you're dividing by n plus 1, which might make it easier to converge. Because this is going to be, the terms are going to be smaller. Here the terms are going to be larger. Okay. So that's how integration and differentiation works. And let's apply this to this function right here. Okay, so for this first one, 1 over 1 minus x squared is, well, think of it this way. If you take, so we're doing this one. If you take this one right here, that's equal to 1 minus x to the negative 1, right? And so if you take the derivative of this, then of course that's going to be the derivative of this one, which is you take the negative 1 down. This reduces by 1 power. Okay, so negative 1 minus 1 is negative 2. And then you have a derivative of the inside part, which is another negative 1 comes out. Those negatives cancel. This can be rewritten as like this. Like that, which is this. So that means that this is the derivative of this. Therefore, its series representation is the derivative of this series representation. So you take the derivative here, n, x and n minus 1. One other thing. You could go from 0, but when you put a 0 here, n is 0, that's going to be gone. So that would be the answer to the first part. Okay. The second part, this is the integral of 1 over 1 plus x. Okay, so you realize that. So what you can do is 1 over 1 plus x is the same as 1 over 1 minus a negative x. And if you compare this and this, you see the only difference is this x has been replaced with a negative x. So you replace all these x's with negative x's. And then this is the integral of this. So you integrate all this. Wait a minute. Hold on. This is a bit confusing, I admit. But okay. You can separate this at negative 1 to the n and x to the n. So you integrate it, you can just leave this. You have this negative 1 to the n separated. Like that. And that would turn out to be the case. Now here, you do have to worry about, so generally when you do integrals like this, you have a constant plus, but this just works out this way. When n equals 0, that is your constant that makes it log of 1 plus x work out. Okay. The inverse tangent. Okay, that's also related to this series. And inverse tangent is related to 1 over 1 minus x as well. You know that if you take the derivative of the inverse tangent, you get 1 over 1 plus x squared. So that means that this is the integral of this. Okay, 1 over 1 plus x squared is equal to 1 over 1 minus a negative x squared. So, so here, if you compare that with this, then the x is just going to be replaced with a negative x squared. So negative x squared to the n. Or like that. Negative 1 to the n, x to the 2n. And the inverse tangent will be the integral of this. So you take the integral of these terms here. And there it is right there. Okay, now, one thing I would like to note right here is that the radius of convergence is 1. That means that these also have radius of convergence 1 because they were obtained by a minor manipulation, that did not change the radius of convergence, and integrating and differentiation don't change taking derivatives doesn't change the radius of convergence, and taking integrals doesn't change the radius of convergence. So none of the operations change the radius of convergence. And so, so let's see up here. We just basically did this. We just derived this right here. And let me just write this down for clarity. So this radius of convergence is 1, and this one's also 1. Okay, this one right here for sine is infinity. And for the exponential function, it's also infinity, and this one's also infinity. This one kind of depends, okay? So I won't worry about that one. I'll write that down. Okay. Any questions at this point? Oh, finally, we get to the exercises. Okay, so finally we get to the exercises. And so you have a little bit of an idea of what to do based on what I've done here, and also, you know, how derivatives and integrals work. So let's do this one, and a little bit of what to look for. So if you see something over something squared, then you know that's a derivative, or that could be a derivative. And if you see things like this, then you know it could be integrals of this kind of thing. Or, you know, of course, you can always go back and just use these formulas here, okay? So let's go, let's do this one first. This one, we want to, the key for something, for something like this is you want to put into the form something over 1 minus something. Okay, that's what you want. So it's really important, in other words, it's important that you have this 1 right here. This is the most important thing. Okay, you get a 1 right there. Here there's a 5, that's good. So what we're going to do is, to get that 1 there, we're going to multiply, wait, we're going to divide each, the numerator and the denominator each by 5. So the numerator is 2/5, and the denominator, when you distribute this 1/5 in, that's a 1. That's a 1 right there, minus x over 5. So that's great because we have our 1 right here. Okay, that's what you go for. And you have a minus, so that's great too. If you had a plus, then that's not a problem because we just say minus a negative and then make this negative. Okay, so that's how we would do that if there was a plus. Okay, so according to the geometric series, so we'll take this numerator all the way out to the front. I'll put it back in later. This will be x over 5 to the n, is what that is. So factor that out, and you have a 1, and then this becomes a 1 also, just factor it out. So 1 over 1 minus x over 5 is going to be this right here. It's going to be that series. And I can put the 2/5 back in. Like that, and we get this. Okay, so that's going to be our series. Now, for the interval of convergence, the geometric series has interval of convergence 1, or radius of convergence 1. However, you have an x over 5. We have an x over 5 in here, and so this will converge when this quantity is less than 1, which is the same as absolute value of x less than 5. So it's going to converge -5 to 5. An interval will go from -5 to 5. That's what it's going to be. And if you check the endpoints, if you put a 5 in here, then you're adding 2/5 repeatedly. And if you put a -5 in here, then you're alternating, it doesn't go to 0, okay? So they don't converge. So the interval is just going to be this. Okay, any questions about this at this point? Okay, let's move on. Number 2. So keep in mind that the goal is to get something over 1 minus something else. Okay, just keep that in mind. And so here we have x squared. Let's put the 16 here because we can divide by 16 and kind of get there. Okay, so divide numerator and denominator by 16. And the numerator becomes x squared over 16. The denominator becomes 1 plus x to the 4th over 16. But you also want a minus here, which is a plus. But like I said mentioned before, you can just change it to a minus, and then you have a negative x to the 4th over 16. Okay. So this becomes all that. And then we can apply the geometric series to it. So factor that out. So what I'm doing is this, basically. Okay. Dang, around space. Okay, so I factored that out all the way. I have 1 over 1 minus something, which means that this is going to be the series. Okay, then I'm just going to put that back in. To get the format that they want. Right there. Now for the interval of convergence, this will converge when this quantity that's being raised to the n is less than 1. Okay. When the absolute value of all this is less than 1. Okay. And that gives you x to the fourth less than 16, which is the same as absolute value of x less than 2. I'm taking fourth roots of both sides. Okay, so that means that our interval of convergence is going to go from it's centered at 0, so it's going to go from -2 to 2. And if you plug in the 2 or -2, they don't converge. Okay, because if you put a 2 in, then this inside part is going to be -16 over 16, which is -1. And then you have a 2 here, which makes this 1/4. So, and then this is alternating, but it doesn't convert to 0. And then -2, it's even worse because it's not even alternating. So they don't work. So that's going to be your interval of convergence. Okay. Great. Any questions at this point? Let's go to number 3. And here you see a square in the denominator, like this, 4 plus x squared. So you immediately should think here, derivative, okay? The derivative works. And indeed, this right here is equal to the derivative of 1 over 4 plus x. Okay, the negative of that. Because when you take the derivative of this one, okay, so the derivative of 1 over 4 plus x, that's 1 plus 4 plus x is the same as 4 plus x. 1 over 4 plus x is the same as that raised to the -1. When you take a derivative, you have a negative coming down like that. And so this is the negative of this. So therefore, this is the negative of the derivative of that. Okay, and then this piece, so let's keep that in mind. We'll apply that in a minute. But this piece right here, again, you want to get a 1 right there. So that's 1/4 over 1 plus x over 4. So dividing everything by 4, you get this. And so you have a 1 right there. And also, I'll factor that 1/4 out just for clarity. Now we can use, we also want to get a minus there. Oops. Okay, so it's minus a negative x over 4. All right, so this will be 1/4, and then n equals 0 to infinity of negative x over 4 to the n. And the 1/4 can go back in. Wait, that's this one. We want to take, we still have to take the derivative. So we want to put it into a form. This is not that easy to take the derivative. Because you got this negative 1/4 there. So let's split everything apart, okay? So first of all, I've got an x to the n, and then I have a -1 to the n. And then I have 1 over 4 to the n, but if I pull this 4 back in, it's 4 to the n plus 1, like that. Okay, so now 1 over, let's go to the next step. So now we're applying this part here. Okay, 1 over 4 plus x is this. So you're applying the negative of the derivative, so negative, and then differentiate this. This negative 1 to the n, the derivative doesn't affect this. Derivative of this is n, x to the n minus 1. And the derivative doesn't affect that either. So you get that. Okay, you have this negative, you put the negative in, and you end up with negative 1 to the n plus 1 by bringing this negative in, times n times x to the n minus 1, all over 4 to the n plus 1. Okay, this should work as the answer. Now it's also asking, what's the radius of convergence? Radius of convergence. So for the radius of convergence, again, you go back to this, less than 1. So the radius is going to be 4. Now I know there's an n plus 1 right here. Okay. But really you should just go back to here. You should just go back to this one. Because where you have the reason you have n plus 1 instead of just an n is because you put this inside. Yeah, that's not going to change whether this converges or diverges. And then again, the derivative is going to have the same radius of convergence as the original. And here we're just taking a derivative, and we're multiplied by negative 1, which is not going to change anything. So the radius of convergence is going to be 4. Okay, and we go on to part B, which is 1 over 4 plus x to the 3rd power. Okay. Now this one is going to be, let's see, if you take the derivative of this, let me do this in red. So the derivative of 4 plus x to the negative 2, which is this one right here, which is we just figured out, that is going to be negative 2 times the 4 plus x, and then you reduce this by 1, that's negative 3. So that's negative 2 over 4 plus x cubed. Okay, so that means 1 over that is equal to negative 1/2 the derivative of 4 plus x to the negative 2. So what that means is if I take the derivative of this, I put that in there. So this is 1 over 4 plus x squared is this. And the derivative of that will be just taking the derivative of this. Okay, so that's going to be negative 1/2. And then I want to take the derivative of this. So you still have the negative 1 to the n plus 1. You still have the n. The only thing is you're taking the derivative right here. So the n minus 1 comes down, and you get x to the n minus 2. And you're still over 4 to the n plus 1. Okay, so let's take this negative 1/2 then. So negative goes in, combines with that one. You get negative 1 to the n plus 2, but that's the same as negative 1 to the n. And then you have an n, and an n minus 1, and an x to the n minus 2. And then in the denominator, you've got this 2 coming in, 2 times 4 to the n plus 1. Okay, so that should work there. And then this last one.
Wait, for part B, would the radius of convergence be the same as the one for part A?
Oh yeah, I'm sorry. Yeah, the radius is still 4.
Okay.
Because you're just taking the derivative. So the radius of convergence is 4. Okay, and then for part C, okay, this is because derivative doesn't change. Okay, and then for this last one, this is just x squared times 1 over 4 plus x to the third. And so essentially, you're taking all of this and multiplying by x squared. And the way to do that would be to just add 2 right here. You leave everything else exactly the same. To the 2. That just comes at, wait, what am I doing? That becomes an n, I'm sorry. So n minus 2 plus 2 is n. So the n goes right here. And again, the radius is still going to be 4. Because multiplying by x squared is not going to change whether it converges or diverges. Because it's just a finite number. Even though it does kind of change the variable thing, the x is. Okay, any questions about that? Okay, let's go to number 4. And here, here's our function. Now recall that we did find the inverse tangent of x to give you this. So this one, you have an x squared. And the inverse tangent of x cubed, if the inverse tangent of x is this, the inverse tangent of x cubed, you just replace this x with an x cubed. So replace it with an x cubed. Okay, so this x cubed goes in right there. It just replaces this right here. And so that's going to give you what, x to the 3. So you multiply this, so 3n plus 3. Oh, it's 6n plus 3. What am I doing? 3 times 2n plus 1 is 6n plus 3. And then you take this in, and that just adds 2 to that. So 6n plus 3 plus 2 is 6n plus 5. Okay, and so that's in. That's that one. And do you remember what I said the radius of convergence was for the inverse tangent was?
It was either 1 or infinity. I remember that.
It's 1. Because this is the integral of something that's 1. So the radius of convergence is still going to be 1. Even if you replace x with an x cubed, still going to have radius 1. It's only if you start replacing it with like x cubed divided by something, or x divided by or x times something, some constant, that you're going to change your radius of convergence. Okay. Yeah, so those are all radius and convergence 1. The other things are infinity, except this one, and that kind of depends on what your k is. Okay, number 5. The natural log of 1 plus x is this, and so we went over this one as well. Here, there's a couple things going on. They want you to take the integral of x cubed times this. So first of all, x cubed log of 1 plus x. That one you get by multiplying this by x cubed, multiplying all the terms by x cubed. So that's a plus 3. Okay, so this right here basically makes that into a plus 3. Okay, so that will be this part. Now, the integral now, of course, when you do integrals, you're going to have a constant, because this is an indefinite integral, so you'll have a constant. So that means that there's many solutions to this, all differing by constant. Okay, so let's see, -1 to the n minus 1, that's a constant, so it doesn't change. The n's a constant. This is what you want to take the antiderivative of this, and that will be x to the n plus 4, and then multiply by n plus 4. Okay, so in other words, the integral of this is going to give you all that part right there. Okay, so just c plus and again, since this is radius of convergence 1, then your radius of convergence is going to be 1.